All right, good day, everyone. Thank you for joining today's webinar on hot water for the food and beverage industry, effective generation, accurate temperature control, process, and washdown for the complete system. My name is Steve Ashby. I'm the Director of Global Food and Pharmaceutical Markets for Armstrong International. Speaking today will be Mr. Tim Clydesdale. He is our industrial sales manager for the Industrial Hot Water Group set of products. Today for the Q&A session, we would ask that you send in all questions in the Q&A tab to all panelists and make sure those questions are public so we can see them. For the purposes of time, we will address those questions through email at the end of today's presentation and as we go throughout the next couple of days. So with that, everyone is muted. So Tim, you're free to go.
Great, Steve. Thank you very much. Yes, good morning, everyone. This is Tim Clydesdale. I want to thank everyone for their time today to spend about an hour with us. I think we have a pretty interesting conversation to share with you. Before we get started, I certainly would like to send out best wishes on behalf of all of the Armstrong family to you, your loved ones and friends. We hope everyone's safe and healthy. So just want to make certain you know that we're thinking of you. So today we want to have a conversation with you, and what we'd like to do is share some knowledge with everyone out there that we have gained over the last 10 years. And this has been pretty interesting. There's been a shift in the thinking of hot water systems overall. And there's some pretty interesting, technology out there that has made some strong headway over the last 10 years. And really in the last 5 years now, it's becoming very in the norm, if you will. And we just want to share with you what we've learned. And when I say that, we work very closely with a lot of consulting engineers who spend most of their time in food and beverage facilities. We also have spent a lot of time and have a lot of good relationships with the end users themselves, including plant managers, process engineers. So again, what we're sharing here with you today is what we have learned from them. Here's a few of the items that we will address today. We want to talk about, hot water in general. Certainly pursue some conversation on, do you perhaps run out of hot water during washdown cycles? That's pretty common conversation that arises in the food and beverage plants. Do you have critical hot water temperatures that cannot be maintained? On the process side, is there too much boiler horsepower available for the steam demands in the plant? Is there too much idling taking place with the existing boilers? Can boiler horsepower keep up with the demand? As plants continue to add capacity, that is a challenge in itself. And how is hot water generated in your plant as a beginning question? So I want to kind of break this down in 3 parts. One, generation using steam, talk about the advantages and the challenges of generating hot water with steam. We want to introduce the steaming methodology, the efficiency of generating hot water, and we'll talk a little bit about alternate options to steam boilers. And then want to review hot water generation and temperature control for the process side, where the the demand is hot water quickly and accurately. So certainly some advantages of generating steam with hot water is that that's what we know. That is what most plants use, have for years. That's available, and it certainly can address higher temperatures of greater than 180 and address a variety of your process needs as far as the high temperature, short time, your clean in place, clean out of place, ingredient water for recipes, and then tank jacketing. These are some pretty common process applications in food beverage plants, and steam is available and can address not only the lower temperature applications, but certainly the higher temperatures as well. The challenges with using steam, the main issue is the efficiency of it. Maintenance and reliability of the system and components is also challenging. It's maintenance intensive. You have your boilers, your boiler feed systems, your steam trap population. Uninsulated steam lines can be an issue, and quite commonly is in plants. Heat exchanger stall, where the equipment becomes flooded and impacts your critical temperatures for process. And just overall parts and pieces in a steam system are pretty maintenance intensive. So here's how our line of thinking is when we look at using a steam boiler and the efficiency in generating hot water. So as you put 100% energy into a boiler, the pretty recognized efficiency is around 80 or 82% of the boiler. However, when you add in other system issues, that efficiency really takes a further dip. And by that, we're talking about inherent boiler loss, radiant losses, blow-down losses, steam leaks, trap losses as far as blow-through traps, scaling within the steam system, heat exchange losses, lost condensate, and air-fuel ratio losses. So when you take in those other inefficiencies, the actual efficiency of generating hot water with a steam boiler is around 60%. And again, this is what we have been told by consulting engineers and plant managers. So with that, we introduce a line of thinking that we refer to as de-steaming methodology. In food and beverage plants, 70% of hot water generation is for washdown and sanitation. That's a pretty interesting number. And this is something, again, that we've heard and we continue to hear. And that's a pretty reliable number there. So this is what we typically see when using steam boilers for generating hot water. This is just what we call a typical feedback heat exchange system. It can be a shell and tube heat exchanger or a plate heat exchanger. And this has some inherent design issues, potential for stall. Certainly, steam and condensate is an aggressive application. a lot of leak points, a lot of overall general maintenance, if you will. And then it's not necessarily fast to respond. As loads swing from high demand to low demand, it takes a while for all of that parts and pieces to get temperatures at a set point, and that lag time can certainly impact everything that it's serving in the plant. So maintenance and reliability on this system, here's again individual parts and pieces that make up these feedback systems. Certainly on the steam side, you have a lot of equipment required, all needing to work in sync to maintain temperatures. Then you've got your heat exchangers, steam traps, other ancillary items such as vacuum breakers and thermostatic valves. And then in a lot of instances, pumps are going to be required. So there's a lot of parts and pieces, a lot of intensive maintenance involved with these feedback designs. So here's the de-steaming methodology conversations as it begins. With some of the shortcomings that were just shared, is there a better way to address sanitary washdown versus using a boiler? And we say there is, and a lot of our, again, consulting engineers and plat folks, will agree. And to make the conversation quite simple, it says everything right here. Direct contact heaters are near 100% efficient versus a steam boiler. With your 100% energy in on your steam boiler, again, a 60% efficiency. We give the same amount of energy to generate hot water by direct contact. We're almost at 100% efficiency. Direct contact heating, there is no idling. It is either on or off. Compared to a steam boiler where the demands fluctuate throughout the day, there's a lot of high use and go to an idle time, and that repeats itself throughout the workday. Talk a little bit more about direct contact heaters. They're atmospheric, so no boiler operator required, no permitting for installations. It's an atmospheric piece of equipment. The water quality is high. So for coming in contact with process equipment, for washdown, water quality remains high. As far as overall dimensions, typically this will be smaller than steam boilers. A lot of the footprints can be pretty minimal depending on the particular design. Very low exhaust temperatures. That venting is cool to the touch. Give you an idea of the efficiency that's taking place in heating the water. And you can fuel these with natural gas or propane. Some more features of direct contact heating. There's no loss out the stack. There's no loss condensate, no idling, and no radiant heat loss. Again, a conversation when comparing steam boilers versus direct contact heaters. And again, that's done at near 100% efficiency. With direct contact heating, there are items that you have to address and be aware of. Must keep metal surfaces below 200 degrees. If you follow this recommendation, scaling is non-existing. Burner outlet pointed downward is a critical feature. This certainly lends itself to superior water. And we must keep inlet temperatures below 100 degrees. Again, that is to prevent scaling issues in the internals of the heater itself. And lastly, but not leastly, recirculation back to the heater is not recommended. Now, with that said, there are applications where recirculation is allowed and works very well. We do an awful lot with bottling companies, and with their bottle warmers, they use a lot of direct contact heaters. That is a recirculated type of system. The temperatures, though, fall within the guidelines that we state here above. So typically the leaving water from our heater into the bottle of warmers is 120. That temperature comes back then recirculating at 80. So we still then stay in a band of acceptance on your water temperatures. We're not coming in to the heater over 100 degrees. Therefore, we're not heating the internal surfaces beyond the 200 degrees. So we avoid the scaling issue, and that is an acceptable application that works quite well in a recirculating manner. Okay, this just kind of gives you a further insight to the internals of the heater and some different options out there as far as different designs. Our heater here on the left, we're the only one, as you'll see, that has the burner and blower that sits on top of the heater and then fires vertically downward. You'll also see in our what we call a flame tube, that flame shoots vertically downward for the central part of the heater body, and you can see there's a piece of pipe there. Call that a flame tube, and that flame then is extinguished completely before it gets at the end of the flame tube. So only the hot gases come out of the flame tube and then move vertically upward where the heat exchange takes place. And that's a critical point to point out, because if you look at the other designs here, everyone comes from the sidewall and they flame quench versus heating with exhaust. And there's a significant water quality improvement when you heat with the exhaust versus flame quenching. So again, we're only heating with gas. So that gas comes down, comes vertically upward. There's Paul rings in a media in that center can that holds heat. And as the water sprinkles vertically downward, hot gases move vertically upward, and that's where your efficiency of near 100% heat transfer takes place. Pretty simple design. The other heaters here as well, with that burner sitting on the side and firing horizontally across, that also, as you can imagine, can cause an issue on the opposite wall. And that opposite wall, gets very hot, and over time of continual operation, that becomes a maintenance issue as you'll get that sidewall failure. And that's a maintenance issue. So again, they're just to show you the differences. Both are generating hot water. Both are generating hot water efficiently. Maintenance issues definitely favor the vertical design as far as minimal maintenance. So if you haven't already thought of this, you certainly would as we move along here. This is a very common question, is water quality. And this is the water quality certifications that our heater abides with. NSF 5 food grade, you've got a USFDA certification, and then equal certification both throughout Europe in the Republic of China. So the water quality, does maintain a high level. So optimum application for direct contact heating. Kind of use a jumping off point at 25,000 gallons per day as where it starts to justify the direct contact heating and the expense of it. Basically 25,000 gallons per day. We're talking over an 8-hour shift, about 50 gallons a minute. So that's, again, what you might use as a guide when you're investigating the use of direct contact heaters. Hot water temperatures in the range of 60 to 185. And the ideal application is generate the hot water, expend it, reheating is not required. And this is what a hot water system looks like, utilizing and generating hot water by direct contact heater. So the heater itself, the bottom can area where you see the small transfer pump coupled, that is not a storage tank, that is a collection basin. So as the water drops to the bottom, at your set temperature, you have to move that to an atmospheric storage tank. The storage tank is what starts and stops the heater. There's level control in the storage tank, and as that level drops to a certain point, it starts the heater, and then the heater just runs for 10 to 15 minutes and fills that tank. So the tanks are sized to go along with the heaters themselves. Since this is an atmospheric system, then coupled to the tanks is a booster pump that's always required to move the water to the points of use. And again, most of the water generated by direct contact addresses the washdown needs in place. So certainly there's going to be host stations that it feeds. It also then, if some process requirements are acceptable using the direct contact water, then there's additional batch vessels, perhaps in other blending of that water to meet other temperature demands. So this just kind of gives you an overview of a typical hot water system using direct contact heaters. Okay, tanks are critical when using direct contact heaters. Again, We generate the hot water, we need to move it to a storage tank. There are some applications where on the smaller heaters, you can make the bottom can of the heater itself a storage tank of sorts, but it's on the smaller heaters. Most of the times, a standalone atmospheric tank is part of the installation. We supply a lot of tanks. Food grade fiberglass tanks are the tanks that we typically recommend. Food grade fiberglass, they're insulated very well and they hold heat very remarkably, if you will. We also supply stainless tanks as required. Okay, your booster pumps, most of the time, this water, as it goes to the tank, then feeds a recirculated loop to your hose drops. So we need to take atmospheric water and pressurize it and move it through that hot water loop. So variable drive packages are also, part of the hot water systems. This maintains flow and pressure in the hot water loop. So when hose stations are activated, they have both the pressure and the desired temperature immediately. Of course, these all change as far as capacity of the heater itself. So the cleaning and sanitation, again, is what's most frequently addressed with direct contact heating. Most of the temperatures we see are in 120 to 140 range. That sometimes goes a bit higher than that, but more times than not, that's the temperature range that customers are looking for. Typically, we hear a plus or minus 5 degrees. If that's the case, just a very simple single temperature type hose station can address this. No mixing valve necessarily required, just an on-off ball valve, then with it feeding your hose in your nozzle. For critical washdown temperatures, then you have to add a thermostatic mixing valve. In these scenarios, typically the water is generated 5 to 10 degrees higher than what the desired washdown temperature is, and then we can blend that with cooler water, and then we can give it very precise temperature for the washdown if that's a critical need. So in the last, again, I'll say about 5 years, we've seen quite a significant, impact on what we do as a company with these hot water systems that we supply. And the demand for automation and controls has really ramped up, in the last few years. So we have been very accommodating. All of the customers want to be able to see what these hot water systems are doing as far as, maintaining temperatures, keeping the amount of water moving through the plant. Want to make certain they can see any faults from the heater and any of the other components that make up these hot water systems. And they want everything, to be accessible via the Ethernet. So all of our equipment and controls, all use Allen Bradley PLCs with all Ethernet connections. So We're very capable of supporting that side of the demands for hot water systems. And I'll say this, that this is always a very important conversation as these projects, move forward. So this is something that, we can accommodate and are very flexible and very good at meeting the customer's individual needs. And the controls really kind of bring it all together, communicate with all the parts and pieces of a hot water system. And this certainly helps your different needs in the plan as far as, operations, the safety side of things, productivity and control as well. Okay, so first part of the conversation has dealt with the sanitation washdown part of a hot water system in a plant. Now I want to talk about more of the process side. Those also have some challenges, and we have some nice answers to some of those challenges. So the first thing when we think process is, very accurate and reliable generation and control for processed water. So we need to get to temperature quickly, and we need to hold temperature once we get there. And this, most of the applications are hot, but this can be tepid water and even chilled water. These are all critical to production, and this is also a challenge in the plants we have found out as well, as far as getting to temperature quickly and then holding that temperature. Briefly mentioned this early on, but again, when we talk about process, these are some of the more typical applications that we see repeat themselves in food plant after food plant. Ingredient water, again, for recipes, we have clean in place, clean out of place, closed loop tank jacketing, recipe water, and process applications requiring precise temperatures. Okay, so here again is our typical feedback heat exchanger. Got a lot of parts and pieces going on here. Steam control valve on the inlet side of the heat exchanger, a controller and a temperature sensor. Got then your heat exchanger, your traps, a lot of times pumps. But what is surprising is a lot of times this setup, there are no pumps. And this probably is one of the biggest nightmare maintenance issues in a process facility, and that is heat exchanger stall. So we can only move condensate 2 feet with 1 pound of pressure. So what a lot of people forget is on these systems, that modulating control valve does exactly that. It modulates pressure in the steam, and if there's not enough pressure to move condensate vertically upward, that's all going to stall. Condensate will back up into the heat exchanger and all that piping, and until the steam pressure doesn't come back and to move that condensate, you're going to have a lot of issues going on there as far as internal scaling of all that equipment. Then when the steam does come back, you have a water hammer issue that just really, wreaks havoc on that whole system. And it just becomes a real maintenance intensive situation, but probably is just as important, if not more, is that the temperatures swing based on high demand and then low demand. You know, it takes a while for this all, the modulating control valve, the temperature sensor, the controller, for all that to communicate with itself and finally get to a set temperature. You know, it takes time, and just can be quite a issue as far as productivity. So again, this is what we call a feedback. So Armstrong has a hot water set that includes heat exchangers and all the pipe, valve, and fitting. And we call this the ReadiTemp. And the ReadiTemp is on the left. And you see that looks a little bit different than the hot water set here to the right. The one on the right, again, requires, it is a feedback system. And our ReadiTemp is a feed forward. And by that, we mean, you know, we control the temperature on the outlet side of the heat exchanger by mixing overheated water with cold water. This will give you a little better idea of what we're doing here with this feed forward system. It's very simple design, less maintenance. All we require is 15-pound constant steam pressure to feed the shell. This omits, in many instances, the need for a condensate pump. With 15-pound pressure, we can lift condensate 30 feet. So not in all instances, but in most of them, we can omit the condensate pump. And then we have overheated water, again, that comes to our mixing valve. And then we blend with cold water. We're able to deliver an immediate temperature on demand. With the constant steam pressure now feeding the heat exchanger, this simplifies the steam supply part of the installation. The constant pressure, we have to reduce the steam pressure down from something, you know, plant pressure greater than 15. We'll take 100-pound steam, reduce it to 15-pound, feeding the shell, and that's it. There's no modulating control valve required. So this is the mixing valve on our ReadiTemps. There are 6 valve sizes, and these are really, you know, items that we really do well with as far as very tight control. All 3/16 stainless steel body, so it's very tolerant, very compatible with RO and DI water. You can set the temperature on the actuator there. On the top of the actuator, you can see there's a keypad. You can set the temperature there at the valve, or you can do it remotely by a 4 to 20 milliamp signal. You can control water temperature from 32 to 212 degrees. You can go to a full cold position or to a full hot. Doesn't have to be you know, some equal parts of mixing. It can be full port, hot or cold, everything in between. So this is a very simple valve. There's not a lot going on as far as parts and pieces all, you know, working in conjunction. Again, we talked about the stainless steel body, and then you can see the bonnet is kind of a concave design. So that is what we call an integral mixing chamber. So as the water come in on your hot and cold side, they then are 90-degree move into the valve body, and it creates a swirling motion in the bonnet area itself. So mixing takes place in the valve itself, continues to mix as it leaves, and we're able to put that temperature probe right in the valve outlet itself. This is a rotary valve, so the only thing that's moving in this valve is the top disc. You'll see the bottom disc secures in the valve body, and then that top disc you can see has a notch cut out of it. That's coupled to the spindle to the stepper motor in the actuator. So the only thing that moves in the valve is that top disc, and all that does is proportion your two water feeds to be at the precise ratio to maintain a set temperature. Again, the rotary design, there's not a lot of maintenance involved. Some seals are in there, but again, there's not a lot of compression. There's not a lot of vertical moving of a stem on a linear valve that can really cause some issues with packings and leaking and a lot of maintenance involved. This valve just doesn't need a lot of attention. So here's a few samples of process applications using steam to water heat exchangers, but are requiring water temperatures to get to a set point quickly and then hold that temperature precisely. We talked about tank jacketing. Most of that is a closed loop application. The ReadiTemps can handle a closed loop application as well as a one pass to a process or a recirculated loop. So on demand, you would always have very precise water temperatures if you had a loop and you were feeding multiple applications. Ingredient water is a very common application. Again, multiple recipes throughout the day, very easy to change the set temperature and again, get up to that temperature and hold it precisely. Certainly improves product throughput. This was a project actually for a pet food facility, and we were able to partner with one of our other divisions, Armstrong Hunt. Here, this was some process coils, again closed loop. So there was, a very small delta T across the ReadiTemp here. On the left, we can provide this with plate heat exchangers as well as shell and tube heat exchangers. I think there was like a 185 temperature required. Again, very small heat loss. So that temperature would come back to our ReadiTemp assembly with only 5 to 10 degrees of heat loss. So again, the way that internals of the valve position those two ports. So in that scenario, the hot port would be almost closed and that water just continues to go right back through to the coils. And all we would do is open that hot water port just a sliver to let enough hot water back in to maintain that set temperature. So it's what can be quite difficult For other heat exchanger packages, it's very easy for us with the Emech valve. Do a lot of support a lot of bakeries with the Emech valve. You can see there up in the right-hand corner in that picture, the blue actuator, and this is for water heating, but not necessarily hot water. So the water temperature is critical in the yeast-raised dough making process, as it affects the rate of activity of the yeast. So common problem is using traditional wax or bimetal thermostats have pretty poor dynamic control action and poor accuracy. So with the Emech valve, with the accurate temperature control, fast payback on improved yield and quality. The perfect dough mix requires not necessarily a hot temperature, but more of a tepid, and the precise temperature to provide the optimal dough temperature is in that 75 to 77 degrees. So again, we're a plus or minus 1 with that valve, so that's very easy to maintain. Of course, the throughput throughout a day is pretty significant. CIP water in this application was pretty impressive. The significant savings have been achieved by replacing an existing water mixing system with an Emech mixing valve. The cycle times were reduced, and the water is within specification more quickly. So we've talked about that. Get to the temperature fast and hold it. They're able to automate the entire system, and the water savings were pretty significant. If you take a look there, estimated at 8,000 gallons, 0.8 million gallons of water that is no longer dumped to the drain on a daily basis. So here we are in conclusion. How you generate hot water for washdown can have a big impact on plant efficiency, energy consumption, and production. De-steaming, when and where it makes sense. Chilled hot water temperature control, accurate control can lead to increased production, quicker batch times, and reduced water waste. So we would suggest that you first address steam boilers, if in fact that's what's being used for generating your washdown water, and that consider direct contact heating for this application and shed that load from existing steam boilers. This would allow you to consider then downsizing the boiler. We're never suggesting getting rid of boilers altogether, because there are steel applications in the plant that require temperatures greater than what direct contact can offer. So there's always going to be a need for steam. For washdown, it makes sense to look at direct contact heating as an option. For your process water, consider feed-forward designed heat exchanger packages featuring the Emech valve for process needs. Again, get to temperature quickly and maintain that set temperature of plus or minus 1 degree. And consider a complete hot water system all engineered items provided with factory startup. And that's really, what we shine on is these hot water systems. We can supply the hot water generation, pumps, storage tanks, hose stations, further process valves for other needs in the plant. We're pretty unique in that regard, and that we not only have the experience and the knowledge of how these systems work and how they can improve productivity, we can actually supply all the parts and pieces. We start up every hot water system that we provide, work with the plant folks, train them on our equipment, and make certain that everything is functioning to the customer's expectations. As Steve shared, we are certainly going to respond to questions, not at this time. What we'll ask is that you reach out to me, and between Steve and I and any others, we will definitely follow up with you and assist in any way we can. So there's my contact information. You have my direct phone number there. Probably the best way right now under the circumstances. We continue to work from home on the sales side. Use my email address to begin the conversation, but then again, Steve and I will definitely follow up in a timely fashion. Also would like to share with you, we as a company will continue supporting the marketplace with webinars. Our next one is scheduled, you'll see here, for May 21st. And this is going to be an interesting one and also probably very helpful. We're going to address a safe and successful startup of a steam system and all what needs to be thought through before that takes place. We have the expertise to lend not only insight but support on that as well, and that will be coming up later this month. So if your time permits and that's a topic of interest, please join us. So that's a conclusion of our conversation this morning. Again, appreciate your time. Please reach out to me if I can offer any assistance. I certainly would like to engage with you. And best wishes moving forward with your business and your companies, but as well as with your families and loved ones, and be very safe. Thank you very much for your time.